Algebra 3, Chapter 4, Section 2, Graphs of Rational Functions. And since we're going to mostly use technology to graph, we should be able to identify asymptotes and sketch them in as dotted lines. You also need to be able to plot any intercepts and a few points to define the shape of the graph. So in other words, whenever you draw a graph, whether you're using your graphing calculator to assist you or not, there are important features of any function that you need to make sure you show. Asymptotes are always going to be an important feature. X and Y intercepts always important, and then you should always graph a few more points to help you actually get the shape of it fairly accurate. Now, some calculators will connect parts of the graph that should be separated, and most of them that do this are the older calculators that are still floating around. I always compare it to drawing with an Etch-a-Sketch. Instead of making a clean break between two branches of a graph, the calculator will just connect the dots, and it kind of looks like they're drawing in the asymptotes, but they're really not. If this is an issue and it bothers you, you can switch to dot mode. What's really important is you need to be aware, if you have an older graphing calculator that will do this, you need to be sure that you leave that out of the graph except to draw in the asymptote as a dotted line. And we also have something called slant asymptotes. When the degree of the denominator is at least 1 and the degree of the numerator is exactly 1 more than the degree of the denominator, the graph will have what's called a slant or an oblique asymptote. So this is a case of bigger on top, which remember, a bigger on top degree has no horizontal asymptotes. If the difference between the two degrees is just 1, if the bigger degree on top is only bigger by 1, then you will have what's called a slant asymptote. And to find it, what you're going to do is you're going to divide. You'll probably have to use long division, although you may be able to use synthetic. But you divide the denominator into the numerator, and the asymptote is going to be the answer to that division problem without the remainder. So you just leave the remainder off, and the answer itself, the quotient itself without the remainder, is the equation of that line. Let's try an example. You're going to state the domain. You're going to identify the intercepts. Remember, the x-intercepts are the places where y equals 0, and the y-intercepts are the places where x equals 0. You're going to find any vertical or horizontal asymptotes, and you're going to sketch the graph. Pause the recording, give this a try, and resume to check your answer. Okay, so here we have everything. The domain we got by setting the denominator equal to 0 and solving. So the domain is all real numbers except that one that makes the denominator 0, which is -2. And you'll notice we sketched a vertical dashed line in at -2. The y-intercept is what you get when you put in 0 for x, which is really easy. And we get 0, 1/2 for that. We have a vertical asymptote, like we said, at x equals -2. And we have a horizontal asymptote at y equals 0. Remember, for horizontal, we're going to use Bobo-Bot needs DC. And this is a case of bigger on bottom, so 0 is going to be our horizontal asymptote. And by the way, this has no x-intercept. There is nowhere where this is actually going to cross the x-axis, because we have a horizontal asymptote that is the x-axis. All right, for this example, we're going to do the same exact thing, a little different problem. So pause the recording, give this a try, and resume to check your answer. All right, so setting the denominator equal to 0 and solving, we discover that there is no place where you can't have an x value. So our domain is going to be all real numbers for x. There is no x that will make that denominator 0. We have an intercept at 0, 0. That is your x and your y-intercept. When you put in 0 for x, you get 0. So that is our x and y-intercept. And for horizontal, Bobo-Bot needs DC. This is a case of eats DC. Exponents are the same. Divide coefficients. 1 over 1 is 1. So we have a horizontal asymptote at y equals 1. All right, now try this problem. Pause the recording, give it a try, and resume to check your answer. Okay, the first thing I did was I factored the denominator because that makes it a whole lot easier to figure out what my domain and where my vertical asymptotes are. And I can also check to make sure that I actually have vertical asymptotes and not a hole instead. My domain is going to be all real numbers except 4 and -1 for x. I have an intercept at 0, 0. If I put in 0 for x, I get 0 for y. So again, my x and y intercept is going to be 0, 0. Those two numbers that cannot be in my domain are going to be vertical asymptotes. There are no holes because nothing would cancel. And my horizontal asymptote, this is, again, Bobo, bigger on bottom, so y equals 0. And there's what the graph looks like. Doing a lot of examples today, but we've really covered the material. We just need to keep practicing. So again, state the domain, identify the intercepts, find any asymptotes, and sketch the graph. Pause the recording, give it a try, and then resume to check your answer. Okay, factoring a little trickier this time. What you needed to do on the bottom was factor by parts. You needed to separate it in half. And you will factor out an x squared, and you'll have x squared times x minus 2. On the second half, you'll factor out a minus x, so or minus 1 rather, excuse me, you'll have minus 1 times x minus 2, which leaves you with x minus 2 times x squared minus 1. Well, x squared minus 1 will factor into x plus 1 times x minus 1. You also need to factor the top, and I'll notice that there is nothing there that will cancel, so I'm only going to have asymptotes and no holes. My domain, I set each of those parentheses on the bottom equal to 0, and I get that x cannot be 2 or 1 or -1. My x-intercepts are going to occur where the equation itself equals 0, and since the bottom is not allowed to equal 0, then what I do is I set the top equal to 0 and solve to find the x-intercepts. And when I do that, I get -1/2, and I get 3 for my x-intercepts. The y-intercept is easier. In fact, if I were you, I would just put 0 into the original equation for all the x's. And when you do that, you get -3/2. So 0, -3/2 is your y-intercept. We already said that the domain, x cannot be 2, 1, or -1, and we have no holes because nothing canceled. So I have vertical asymptotes at all 3 of those x values. And this is another Bobo, bigger on bottom, which means I'm going to have a horizontal asymptote of 0. And there's what the graph looks like. Kind of an odd looking thing. All right, now try this problem. Now this time you're going to have a slant asymptote. So remember, what you're going to do is you're going to divide the denominator into the numerator, and the quotient without the remainder gives you the slant asymptote, which you will then graph as a dotted line. Pause the recording, give this a try, and resume to check your answer. Okay, now one way to do this is you can separate it. It's x minus 9 over x. Actually, that's what you get when you do the division. So the domain, all real numbers except x equals 0. Your x-intercepts are where the top will equal 0, which is at -3 and +3. If you factor x squared minus 9, you get x plus 3 times x minus 3. We have a vertical asymptote at x equals 0, and we have a slant asymptote at y equals x. That's what we got when we divided. When we divided x into x squared minus 9, we got x minus 9 over x. 9 over x would be the remainder. So x is our slant asymptote, or y equals x. And there we go. So we have a vertical asymptote at x equals 0, which is the y-axis. We have the slant asymptote and the line y equals x. And then you can see the intercepts there, and you can see how the graph follows both of those asymptotes. Okay, let's try another one. This again is going to have a slant asymptote. Pause the recording, give it a try, and resume to check your answer. Again, the first thing we do is we divide x squared minus 4 into x cubed, and we get x plus a remainder of 4x over x squared minus 4, which that part really doesn't matter to us. What we're interested in is the x. We don't need the remainder. The domain is all real numbers except positive and negative 2, because when you factor the denominator, you get x plus 2 times x minus 2, so x cannot be plus or minus 2. We have an intercept at 0, 0. If you set the numerator equal to 0, then you get that x is 0, or if you put in 0 for x, you get that y is 0. So our x and y intercept is at 0, 0. We have a vertical asymptote, or 2 rather, at plus and minus 2, and the slant asymptote at y equals x. And this is what it looks like when we graph it. Now you may be wondering, okay, I thought asymptotes, they weren't supposed to cross it. They actually can briefly. Part of the graph can. It is possible. And in this case, it does. It won't be a big thing. It usually only happens with the slant asymptote if it's going to happen. But it should just be a one-time occurrence if it does. All right, let's try a word problem. It says a page that is x inches wide and y inches high contains 30 square inches of print. The top and bottom margins are 1 each deep, and the margins on each side are 2 inches wide. We want to show that the total area on the page is a equals 2x times x plus 11 over x minus 4. We want to determine the domain based on the physical constraints of the problem. And we want to graph the area function and approximate the page size for which the least amount of paper is used. All right, that's a lot to do there. Now you've got a picture, it's labeled. It's not completely labeled. You're going to need to figure out the print area. Remember that the width of it is x, and the length is, and the height of it's y. And you're going to need to subtract out the margins to find the print area, and then multiply to find the print area. So pause the recording, give this a try, and resume to check your answer. Okay, there was a lot to this. We know that the area is xy, and we know that the print area is 30. In other words, x minus 4 times y minus 2 is 30. So solving for y, we get y minus 2 is 30 over x minus 4, and then we added 2. And then what they did there is they combined the 2 plus 30 over x minus 4. They gave it the common denominator of x minus 4 and combined it into one fraction. So the area is x times y, but we're going to substitute 2x plus 22 over x minus 4 for y, because we only want one variable. And so we have x times 2x plus 22 over x minus 4. And then what they did is they went ahead and multiplied the x through, and they actually also factored out a 2 there. So you have 2x times x plus 11 over x minus 4. And it says since the left and right hand margins are 2 inches, x has got to be greater than 4, because if x were any less, there would be no width for you to print on. Since the margins to either side have to be 2 inches, you've got 4 inches of margin. So the paper's got to be more than 4 inches wide if you're going to be able to write anything on it. So x has got to be greater than 4. And then finally you have the graph there, and the area is at a minimum. Look, you're looking at the minimum on the graph, the low point, when x is about 11.75 and y is about 5.87.